Good morning, everyone. My name is Seonhi Ro. I'm Manufacturing Industry 4.0 Specialist at Ford. Probably quick introduction for myself. I'm more than 20 years at Ford, started as a powertrain integration engineer and moved to the Industry 4.0 area. My background is mechanical engineering. So today I want to speak about how Ford Motor Company is facilitating an evolution to Industry 5.0. So I will start with the definition for Industry 4.0, 5.0, and then we will speak about automotive industry transformation phases. The main part of my presentation is in the product lifecycle management, which I will give you a specific practical examples what we implemented. And finally, if we apply all these technologies, how the factory of future looks like. And then after that, we will go to Q&A session. So I think most of you are already aware what is Industry 4.0, but in order to get same basis, let me quickly go through it. The first industrial revolution is production facility infrastructure revolution using the water power. And second industrial revolution is mass production with conveyor belt using the electricity. Here, the Henry Ford was main contributor, which we are very proud of. And then the third industrial revolution is automatization using the electronic and IT. Now the fourth industrial revolution is cyber physical system using the complete digitalization and the net connection. Here we see, the cyber is internet and the physical things is things, so we are talking about Internet of Things. Now the European Union is defining the Industry 5.0. So the background is we industries are focusing very much in the economical growth and efficiency, productivity. But with the time, we are recognizing there is something missing where we are human beings in that technology. And we are recognizing also there is the limitations of planetary resources and so on. So that's why the European Union defined the Industry 5.0. Yesterday, there was a lot of sessions with that definition. But to summarize it, the Industry 5.0 is, in my opinion, it's not really technical revolution, but it is more complementary to Industry 4.0. We are defining the focus area. So first focus area is sustainable. Sustainable leads the actions on sustainability and also respect planetary boundaries. And second focus point is human-centric. So that means promotes talents and diversity and empowerment to the people. And also the last focus area is resilient. That means resilient, agile, and resilient with the flexible and adaptable technologies. So now let's get to the automotive industry transformation. We are at the moment transporting to the CASE, C-A-S-E. So C stands for connected, A stands for autonomous, and S stands for shared, and E stands for electric. In order to get the sustainable business, we need to have a robust product lifecycle management using the Industry 4.0 technology. So now let's speak about the product lifecycle. if we talk about the product life cycle, we are starting design phases, so 11 o'clock direction, if you see in the circle. So we are starting design the vehicles, and parallel to is running the procurement. And if we produce the vehicle, and the vehicle is transported to the customer, that's the blue color now, and then if the customer uses the vehicle, the parts are remanufactured or recycled. That's closing the cycle. So during this life cycle of the vehicle, we have a lot of data, but we are not using completely this data. It is even not connected, those data. So if we can connect those data each life cycle, we can have a lot of benefits and to have a very robust product life cycle management. So there are some examples, practical examples I will go through, the generative design, and also in the production phases, AR, VR, different things, and the different technology, especially AI and the blockchain or wireless communication that is going through whole life cycle. So let's start with the example, generative design. What is generative design? Generative design is autonomous geometric design after specification and constraints. There's three categories. First is topology optimization. Second is biomimicry. Third is morphogenesis. So the top right-hand side, if you see it, in the topology optimization. In the topology optimization is you are taking the materials where the material is not loaded. If you see top right side, this example, top is the conventional design. You have the holes and the whole material is filled. But between those holes is that area where the material is not loaded. So you can take out those materials, some iteration. You can get the last, the design, which has a much less material, and that means much less weight. And the second example is biomimicry. Biomimicry is we are optimizing our design after nature behavior. It's like first trees or leaf structure or bone structures. And the third category, morphogenesis, is a little opposite to topology. We are adding the material if the area is loaded. So it is more additive rather than the subtractive. So you can use the different software, which is listed on the bottom, your software, and then you can create those designs. Because this design use the less material, it is very sustainable. But these designs are sometimes very difficult to produce with our conventional production method. So now that is coming why we have the next, the additive manufacturing. So 3D printing we're talking about here first. And then if you see the right-hand corner, that there is an example what we have done. So that is the tool in the factory. It is transporting IP part, and that part is optimized, topology optimized. You see this white part, that is topology optimized with a polymer material, not anymore metal material. And we can produce it very fast, and it is much lighter. So if we go to polymer material additive manufacturing, that is the state of application. A lot of examples we have already. But if we talk about metal additive manufacturing, it's progressing. And in the research phases, there is also talking about 4D printing, which we are not applying at the moment, but I will quickly go through what it is. It is You print out this flat, the drawings of the cubicle, and you put your part in some conditions. In this case is the fluid, so your boundary material is shrinking much faster than other materials, so it is assembling itself. You don't need to assemble with the manpower, it is assembling automatically. And then what we are using this additive manufacturing is today's mainly the toolings or the prototypes or low volume production. But we want to also use this in the high volume production. So, but there is still some work needed to be done because the pre-processing and the post-processing process in the additive manufacturing is a lot of things are still manual. It costs a lot of money. So we are working on it. And then virtual reality, augmented reality. So in the product development phases, it's standard to using virtual reality. So first example is the car you can put in some room virtually, and the people can, with the glasses, go and feel the vehicles, and they can give very early phases your design feedback. So we can get very early phases feedback from the customer. Oh, it's good, it's not good, or it's not practical, or whatever. And not only in the product development phases, but also in the process development phases, in the production planning, we are using also this 3D, the virtual reality, that different location of the world, they can work together, and also even the operator can give the feedback what design is not economical. And we are using also this virtual training. It is an important point because before we have physical part, the operator can build the car and they will give us the feedback and it is changes. So if you have already physical part later, then it is cost a lot of money to change it. But in these phases, you can change in the virtual model. Even in the bottom right-hand side, you can see if we put some sensors, then they can also measure the forces, which force the operator is requiring. So it's an economic assessment is done also very early phases. So all changes can be done in the very early phases, which is very human-centric and also sustainable, because after you have the physical parts and you need to change something, it's a lot of scrap and you need to have a lot of stress. So it's make us much more resilient. And then the virtual commissioning. If we build our production line, we order our vendors, the machines, and normally you go to the location before they sending the machines. So they checking everything, but before we do the physical commissioning, we can do in the virtually. So we have a production layout, and then the supplier vendor can send us their dynamic models, and then we can plug it, check it, everything, if it is no conflict, and then after that, and also during the development, you can also change something which is not fit. So it will make, in the physical commissioning, much faster and with a very low risk. So, and then we have a workstation readiness virtually, and also dynamic plant simulation, and also the workload of each station we are checking. So I need to get some water. And this is all things are basis to make a digital twin. So I will quickly go through. It is a very complicated process, but it will need also, each process has some iterations. I started with what is required in the digital twin. Digital twin requires complete and granular actual, the virtual representation. So how we do it? We're talking about a lot of digital twins, but generally we can have the product digital twin, we can have a production digital twin, and then after that we have the vehicle, we can have the digital twin, how our vehicles are moving in the, on the street. So I'm focusing on here more product digital twin, but normally before you can do production digital twin, you need to have product digital twin. So if we have a virtual product, CAD, models, everything, then you have simulation, and then you are testing the product and verify your product virtual model the testing. But parallel to that, you need to make sure this product you are testing, you can produce it. It is high level. You're doing also production testing and also simulation. And then you have a 3D, your factory models where you want to build your factory, and then verify which the production simulation, what you have done, is going into this space, and then you are assessing the verification high level, and then you get also the models from the supplier, the machine is dynamic models. You put that all together, and also whole process workstation analysis, then you can get all the digital twins, dynamic digital twins as a virtual model. But it is still not breathing. A lot of people saying here is digital twin. That is still not digital twin. It is not breathing. You can make your digital twin only live. You breathing with the data, real-time data. That's the next step. You build your factory, and then you have the real-time data, how it is, which data is coming, and then you compare what you have done until now, and then that is feeding to your virtual model, and you are reflecting your virtual model is corresponding to your real model. So it's now getting the digital twin. So it is still, I think, a very long way to work. And this is now the process if you have the new product and the greenfield. But if you go to the existing lines, so you can take some of these actions. So that is a big advantage for the digital twin is if you have the digital twin, if you want to change something, you can do first with your digital twin the changes and recognize what is the problem which we cannot image it, and you can see already in the digitally, and then change your concept, and then you change the physical changes. So it is now, again, the human-centric and the resilient. And also, because we do not scrap all these materials before physical change is happening, so that's also sustainable. So I have some videos here for cobots. We are using in cobots in your Cologne vehicle plant. And the operator is cooperating with the robots. That's the collaborate robots that we're saying cobots. And then they are installing the shock absorber. And so even they can drink coffee together. Okay, the next example is our AGV, that is the Valencia engine plant. So Eduardo is also here. So this example we will show you.
The main duties for the robot is to deliver the spare parts to all the station in the line, in this case in body and stamping. This autonomous robot doesn't need any external guide to navigate. We call him survival because the intention was to avoid hazards.
Let's make this love robotic.
Okay, then we have examples, the drone, which is applied to Dagenham engine
What
plant.
if you could do potentially dangerous but essential tasks absolutely risk-free? A group of Ford workers are flying drones around their factory to do just this. To carry out vital safety inspections of high-up or hard-to-reach places, Dagenham engine plant workers are using drones with cameras to safely and efficiently inspect machinery and roof areas.
We wanted to take the risk of these inspections away from the employee. By using a drone, we can do that.
Previously, staff had to climb scaffolds to check 40-meter-long overhead gantries. Now, maintenance staff can zoom in on each area with feet firmly on the ground. The whole production facility can be covered in a day by controlling drones equipped with GoPro cameras to thoroughly inspect each area, ensuring they're well maintained and comply to rigorous safety standards.
Okay, then we have an example which we applied in the US, a cooperation with Boston Dynamics.
Busy day at work. Fluffy, come here. Good dog.
I'm Mark Goddard in the Advanced Manufacturing Center here at Ford Motor Company. I'm the Digital Engineering Manager, and I'd like to introduce Fluffy, our quadruped robotic dog. So this is a Boston Dynamics Spot. We've nicknamed him Fluffy, and we're utilizing it to actually do laser scans of our facility. That image is then utilized by our engineers to develop new vehicle programs, and it allows them to develop more accurate layout of our facilities. These cutting-edge technologies allow Ford Motor Company engineers to save money, retool facilities faster, and bring new vehicles to market sooner.
Hi, my name is Paula Wiebelhaus. I'm Fluffy's handler. Considering I've never had a game controller in my hand before I received Fluffy, at first I'm not gonna lie, it was kind of intimidating to be in control of a dog that is this high tech, but he is easy to operate and he maneuvers well through spaces. He'll go into some tight areas that Scout, our other robot, won't be able to accommodate. I have never owned a dog before in my whole entire life, so this is our first entry into dog ownership. Like people bond with their cars or certain tools in their workshop, I certainly have bonded with my companion dog, Fluffy.
Fluffy definitely has a coolness factor. So it's been amazing to be able to take something like Fluffy and turn it into a usable engineering tool for our company. The opportunity here and what this robot dog can do is significantly going to change the engineering community. It also gets people excited about the fact that we're on cutting edge technology here at Ford Motor Company.
Okay, then we have the blockchain examples. Blockchain is used at the beginning in the Bitcoin. And this all in the blockchain, all participants in the value chain approve their ledgers. It is like a fingerprint of the product. So advantage is very clear and safe documentation, but it still needs a lot of computer capacity. So the pilot we are doing is AI combining the blockchain. So here we show an example. From the raw material until through the tier 3 to 4 or suppliers to us, and then dealership and the customer, and the end of the life cycle. So an example, batteries, we can put the battery examples and we can follow exactly which origin have these raw materials. So it is also for an example, CO2 footprint, you can do this way. So the data is transporting, only necessary data is transporting to all life cycle. And then we have the 5G example. Is in Danton
We've got a long history of manufacturing vehicles with internal combustion engine technology, but we're in a process of total transformation. For us in Ford Motor Company in Europe, we're ready to deliver that significant pace of change in terms of the adoption of plug-in and fully electric vehicles.
We have to very rapidly redeploy all of the assets that we've got into factories that can meet low carbon vehicles by 2030. The factory of the future is all about moving data, and 5G is an enabler for that. Ford has a long-standing partnership with Vodafone. Building a pilot line with 5G was a great opportunity for us to then look at the technology, understand the technology, and without this learning, we wouldn't be able to consider doing this in one of our plants.
One of the use cases here in Dunton, using the Vodafone mobile private network, is on our welding machines. So we're capturing images before we're welding and then after we're welding. And then we can use AI and feed back to the machine if the weld isn't particularly good, and then change and re-weld whilst the part is still in the machine. You could be welding and creating terabytes of data very, very quickly. So it's important that we have the connectivity that can keep up with that and that could send that data and store it as quick as we're producing it.
We've been able to see data back from the laser process that tells us that we're getting a buildup of heat in our lenses, which means that we need to replace them. We could then contact an expert to discuss it, but we can also use the 5G network in conjunction with a HoloLens system to guide an operator through the process of changing that lens. We're keen to make sure that we can connect securely, and of course with 5G you have the ability to use SIMs on every single device and make sure that you're aware of every device that's communicating on your private network.
We've got plans to totally transform our vehicle lineup over the next 10 to 15 years. The manufacturing engineering team are at the centre of the change of EV powertrain in Europe, and this team needs to work with people like Vodafone so we can do that as efficiently as possible.
Okay, to summarize, so how the factory of the future looks like if we apply all these technologies. So first, we will have the planning and the execution with a real-time track and trace. So you as a customer, you order in the online the vehicles, then you can see it is planning phases or it is already in the body shop, it's assembly, and everything you can see it, and even you, and also you can get the delivery time. So it's all connected. And there will be self-monitoring and self-adaptive logistics with the different using different technologies. And also in the intra-logistics, smart shelves, or it's autonomous driving in the factory, and the inventory is monitored, and if it is less material, then they order automatically. And also wireless communication is part of them. And the production, we will have AI optimized, built, and flexible integrated production plan and execution. So predictive maintenance and predictive quality, which will lead to near to zero failure and to get high efficiency. And the digital twin will be part of them, IoT, real-time track and trace, and cloud and edge computing, and also integration with AI and human interaction. It's very important part. And the robust product lifecycle management in the blockchain and AI that will give us a sustainable business. So the future factory will be human-centered and resilient and sustainable. Thank you very much. So any questions? No question? Okay. So you can contact me through the LinkedIn, whatever. So if you have any question later, contact me. Okay, thank you very much.